A warm welcome to part 5 of the lecture on functions. In the previous lecture, we learnt about one-one and many-to-one functions, onto or surjective functions, bijective functions, and finally the inverse of a bijective function. In this lecture, we shall study about even and odd functions. So let's start. We shall mainly be concerned with a real valued function of a single real variable. So let f be a function from a to b, where both a and b are subsets of R. F is said to be an even function if the following two conditions are met. For every x belonging to the domain A, minus x must also belong to A, and f of minus x should be equal to f of x. F is said to be an odd function if, again, for every x belonging to the domain A, minus x must also belong to A, and f of minus x should be equal to minus of fx for every x in the domain. Let us look at some examples of even functions. The first example is that of a constant function f from R to R such that x maps onto a constant number c. It is very easy to check why it is an even function, because our domain is the whole of R. So for every x, minus x also belongs to R. And since the function maps every x to a constant, therefore f of x is equal to f of minus x for every x belonging to R. Similarly, let us consider the cos function f from R to R such that f of x is equal to cos of x. We are well aware from our elementary trigonometry knowledge that cos of x is equal to cos of minus x. So this is also an example of an even function. Let us look at yet another example, f from R to R such that f of x is equal to mod of x. Why is this an even function? You can verify it directly by using the definition of mod of x which was provided in one of the earlier lectures. But a better way to go about it is to consider it geometrically. We know that mod of x is the distance of the point x from the origin, as shown in the figure. Now for every x, the distance of x from the origin is same as the distance of the point minus x from the origin. Therefore, by definition, modulus of x should be equal to modulus of minus x, because both x and minus x are situated at the same distance from the origin. Therefore, mod x equal to mod of minus x. Hence, the absolute value function or the modulus function is an even function. Consider another example, f from R to R such that f of x is equal to x square. It is very easy to check why this is an even function, and I will leave it to you. Consider this function f from the semi-closed interval 0, infinity to R such that f of x is equal to cos x. Now this function is not even, despite the correspondence rule being that of the cosine. Why is that? This is because the first condition for a function to be even is not met, because corresponding to a point say 1 in the domain, the point minus 1 does not lie in the domain, because we have restricted the domain to be a set of all non-negative real numbers. Therefore, the first condition is not met, and hence this function is not an even function. For the very same reason, the modulus function restricted to the semi-closed interval 0, infinity is also not even. Therefore, our conclusion is the following. Whether a function is even or not does not only depend upon the correspondence rule but also on the domain of the function. As we have just seen, for the same correspondence rule, that is mod of x, one of the earlier functions was even, but this one is not even. Now let us look at some examples of odd functions. The first and the most common example is that of the identity function f from R to R such that f of x is equal to x. It is a trivial exercise to check why is this function an odd function, and I shall leave it to you. Similarly, the function f from R to R such that f of x is equal to sine x is an example of an odd function because we know that sine of x is equal to minus of sine minus x from our basic trigonometry knowledge. Therefore, this function is an example of an odd function. Similarly, consider this function f from R to R such that f of x is equal to e to the power x minus e to the power minus x by 2. As you can easily check by substituting minus x in place of x that this function is an example of an odd function. Similarly, the function f from the open interval minus pi by 2 comma pi by 2 to R given by f of x equal to tan x is also an example of an odd function because tan minus x is minus tan of x. Now, let us look at some functions which are not odd. F from the closed interval 0 comma pi to R such that fx is equal to sin x. Clearly, the first condition for a function to be odd is not satisfied because there is no negative number corresponding to a positive number in the domain. Similarly, the function f from R to R such that fx is equal to x when x is greater than equal to 0 and x square when x is strictly less than 0 is also not an example of an odd function. Because as you can check, f of 1 is equal to 1 and f of minus 1 is also equal to 1. Therefore, f of minus 1 is not equal to minus of f of 1. Hence, the second condition is not met and therefore this function is not an example of an odd function. Let us take a small exercise. If f is an odd function and say 0 belongs to the domain of f, then what is the value of f of 0? If you wish to give it a shot, you may pause the video for some time and try to solve it yourself. The solution is as follows. Since f is given to be an odd function and 0 belongs to the domain of f, therefore from condition 2 it follows immediately that f of 0 is equal to minus of f of 0, which means 2 times f of 0 is equal to 0 and hence f of 0 is equal to 0. Therefore, the value of any odd function at the origin is equal to 0 provided 0 belongs to the domain of the function. Now we wish to understand the nature of graph of an even and odd function. Let us start with even functions first. Since an even function f takes the same value at x and minus x, or in other words, since x and minus x have the same image, the graph of f is symmetrical about the y-axis. For example, consider the constant function fx equal to c. As you can see, the graph of the function in the left half side of the plane, which is this, is nothing but the mirror image of the graph on the right hand side of the plane. So the right hand side of the plane is this, and the graph in the right hand side of the plane is just this horizontal line segment. The graph on the left hand side, as you can see, is nothing but the mirror image of this portion with respect to the y-axis. Consider the absolute value function fx equal to mod x for all x belonging to R. By definition, mod x is equal to x when x is greater than equal to 0 and minus x when x is less than 0. Therefore, the graph of mod x has this shape, which is that of V. Now it is easy to see that the graph of mod x in the left hand side of the plane, which is this portion, is nothing but the mirror image of the graph on the right hand side of the plane with respect to the vertical axis. Since for an odd function f of minus x is equal to minus fx, we say that the graph of f is symmetrical about the origin. By being symmetrical about the origin, we mean the following. The graph of f in the left-hand plane, which is denoted by LHP, is obtained from the graph of f in the RHP by first reflecting it about the y-axis and then reflecting the image about the x-axis. As an example, consider the identity function fx equal to x for all x belonging to R. The graph of the identity function is the straight line y equal to x. Now consider the graph of f in the right hand side of the plane, which is just this segment. Now if we reflect this segment about the y-axis, we get something like this. Now if we reflect this image with respect to the x-axis, we get this, which is nothing but the graph of the identity function in the left half plane, as you can check. At this point, let me make an important remark. Any real valued function of a single real variable can be written uniquely as the sum of an even and odd functions. That is, f of x can be written as odd of x plus even of x, where odd of x is a function which is called the odd part of f, and even of x is a function which is called the even part of f. As the name suggests, odd of x is an odd function and even of x is an even function. Let us figure out what these odd and even parts of the function f are. F of x is equal to odd of x plus even of x. Therefore, f of minus x is equal to odd of minus x plus even of minus x. Since odd of x is an odd function, therefore odd of minus x is minus odd of x, and even of minus x, since it is an even function, will be equal to even of x. Now if we add equations 1 and 2, we get f of x plus f of minus x equal to 2 times even of x, which implies that even of x is equal to f of x plus f of minus x by 2. Similarly, subtracting 2 from 1, we obtain odd of x equal to f of x minus f of minus x by 2. Now it's a trivial exercise to verify that even of x and odd of x are indeed even functions and odd functions respectively. Let us take an example. Let f be a function from R to R defined in the following way. F of x is equal to x if 0 is less than equal to x is less than equal to 1 and 0 otherwise. The graph of the function will look like this. It will be the straight line segment y equal to x in the closed interval 0 to 1, and at any other point the value of the function will be equal to 0. So f of x will look like this. It is 0 at all other points except the closed interval 0, 1. And in the closed interval 0, 1, it takes the value x. Therefore, the graph of f looks like this in this particular interval. Now we wish to find out the even and odd parts of f. So for that, we will first need to find out what is the function f of minus x. F of minus x can be found out by just reflecting the graph of f about the y-axis. I leave it to you, and I will provide the final expression for the function f of minus x. F of minus x will be defined in the following way. F of minus x is equal to minus of x when x belongs to the closed interval minus 1, 0 and 0 otherwise. So f of minus x has the following graph. It is equal to the segment y equal to minus x in the closed interval minus 1, 0 and 0 everywhere else. By definition, even of x is equal to f of x plus f of minus x by 2. So we need to add this function with this one to obtain the even of x, and finally we will have to divide the sum by 2 in order to get the even part of x. So once we add f of x and f of minus x and divide by 2, we obtain a function whose graph will look like this. It is equal to the segment y equal to x by 2 in the closed interval 0, 1 and y equal to minus x by 2 in the closed interval minus 1, 0, and at every other point the function will be equal to 0. So the even part of f will be this function. The odd part of x is given by the expression f of x minus f of minus x by 2. We already have the graphs of f of x and f of minus x. So if we subtract the two functions and divide the difference by 2, we get a function whose graph looks like this. It is equal to y equal to x by 2 in the closed interval minus 1 to 1, and for every other x it is equal to 0. So this is my graph of odd of x. Now let us add the function odd of x plus even of x. So even of x has this graph, as we have already seen, and the odd of x has this graph, which we have just seen. Now if you add these two graphs, you get a function whose graph will be equal to this. Please notice that the graph in the left hand side of the plane cancels each other. So f is 0 for any x less than equal to 0. So these two portions are additive inverses of each other, so to say. They will add up to give you 0. Portion on the right hand side will add to give a graph which looks like this: y equal to x in the closed interval 0, 1. Now it is easy to see that the sum of the odd and even parts of x is nothing but my original function f, which we had taken in the beginning. I will stop at this point, and in the next lecture we will learn about periodic and aperiodic functions, which in my opinion is a very tricky concept. So thank you.